Earlier you talked about some of the early successes, early examples of computer vision, innovation, moving from the research environment into industry, some of the movie special effects and video games. What more recent examples strike you as being particularly significant innovations moving from the research world into industry?
Okay, so currently probably one of the hottest items from the last year is the Kinect from Microsoft.
Yes.
And so it's really based on the use of recognition technology, starting with range images. So their innovation, one of their innovations was that instead of just using a regular RGB camera, you'll also get depth information.
Yeah.
So sensors like that have, by the way, been around for years. I mean, in the 70s there were range sensing devices, and they've always been there in the background. But one key thing now is that you can do them quite cheap.
Right.
I mean, each you can build a sensor. The camera which is being used in the Kinect has to be at a price point that you can embed it, that you can have it in every consumer unit, right?
Yes.
So but that's happened as a result of the general progress of hardware. Then the algorithms that they've used, obviously some of the details are proprietary, but they have published the essentials of the algorithm. These are basically machine learning type approaches. I mean, they use decision trees to train, to take an image and identify which are the pixels corresponding to a person. Then of those pixels, what pixels correspond to the upper arm, lower arm, torso, etc. And with that, they can build a kind of a stick figure model of the person. And once you have that, you kind of have the right interface for somebody designing a game, because you can infer the stick figure corresponding to the person, right? And you don't need to put any sensors on the person. It makes it very convenient for people, because people don't want to wear lots of gizmos on their body to do this. So this is, I consider, a clear success of computer vision, and it's based on object recognition techniques. The same techniques, if we had applied them to RGB images, just intensity images, our error rates would be much higher. If you use range images, our error rates are much lower. So I, as a researcher, am in fact really interested in solving the problem for given just RGB images, because clearly humans can do it, and I'm sure that one day our algorithms will. However, if you want a system which is going to be useful today, then why not get the extra help provided by having range information?
Right.
And that's what the Microsoft group did. And I think it's a beautiful success of computer vision.
Yeah. As computer vision is increasingly in the lives of everyday consumers, Microsoft Kinect, face detection cameras, vision-based automotive safety, what are some of the common misconceptions that you find people have about computer vision?
Okay, the first and foremost one is that people think that it's easy and it is done. Okay, because I mean, they see these movies, right? I mean, in Star Trek it can always be done. So I mean, it's crazy. It's kind of the first thing I have to do when I'm talking to a lay person is really to convince them that this is in fact a hard and difficult problem, because the environment has changed. We are now used to computers being there in our environment. In everybody's home there might be 10 computers, hundreds of computers, whatever. If you count all the very little microprocessors, we might have thousands of computers in our home, right? So we live in a world where computers are ubiquitous, and we have seen these movies. I mean, we have seen, the Terminator movies, and, the Schwarzenegger character has clearly innate computer vision system, right, which is amazingly effective. And because in everyday life we see computers effective at all the other things we use them for, somehow people make the jump to thinking that these tasks of processing and analyzing images are equally easy.
Plus, we ourselves do it effortlessly.
And we ourselves do it effortlessly. So the reason why we do it effortlessly is because through a billion years of evolution, the system is hardwired. You have a considerable evolutionary pressure to develop a good vision system. Those tigers who couldn't see their prey didn't get food, so they died. Those prey who couldn't detect the tiger, they also got eaten and they died. There's a pressure to evolve a good vision system which works fast and is reliable and so forth. And then of course there is something which you are born with and then you learn, the child learns. So a 2-year-old or a 3-year-old child has an amazing visual system. Now we tend to think that somehow the ability to play chess is difficult or the ability to prove theorems is difficult, but the most amazing achievements of intelligence are what a 3-year-old child can do. Those are the hardest to automate, and vision is one of those. And unfortunately, the first thing which I have to do when I talk to a layperson is to convince them that the problems that I work on are difficult. Everybody buys that they are important, but they just assume that it has already been solved or it must have been easy. Okay, so that's the first thing we get past. Once we got past that, and I think that essentially you can do this by trying to take them through to what it would take. Once you get to the stage of trying to see how you would write a computer program which would process an image, once we can get to those stages, to thinking in those steps, then you see, you want to recognize a face. Okay, detect a face. But the face may not be in the same position. The lighting may not be the same. How do you manage to write a computer program which will do it right in spite of all these variations? Then people start to appreciate the difficulty of the problem.
Right. Now, take it from another angle, as the computer power increases, and the way you were describing it earlier put me in the mind of wireless, right? You'd say something similar 20 years ago about wireless, where we had all these ideas about CDMA and OFDM and so on, but we didn't have the ability to implement it, in a small enough and inexpensive enough package that it could be widely deployed. And then the semiconductors caught up, and now everyone has it in their pocket. As the computing power and the sensors and so on make it increasingly possible to embed computer vision in all kinds of products, what advice do you have for people in industry who are thinking about, I see what's going on here and here in some of the advanced products and in the research. I want to incorporate some of these capabilities into my product. And in particular, what I've seen is there's just such a vast mountain of research papers and textbooks and so on out there. It's really tough for someone who hasn't already got their PhD and become a specialist in vision to get their arms around it, figure out what's real here and what's realistic and how does this stuff work. So what advice do you have for people in industry who are not specialists but are starting to think about and get excited about what they can do with vision capabilities in their systems?
Good question. I think this is a challenge, and because the best stuff, what current capability you can only find out by going to the latest conferences. So if you want to know what's at the cutting edge, the best strategy I think is to go to the computer vision conferences. So if you go to a conference like CVPR, which is IEEE conference on computer vision and pattern recognition, or ICCV, which is the International Conference in Computer Vision, and if you attend the talks there or you look at the proceedings, that will give a sense of what's what the cutting edge is. But those are not necessarily the techniques which you can deploy in products, because that's the cutting edge. That's where the stuff sort of half works, or it works enough for us to publish a paper, but it's not really. It may not be mature enough to actually be deployed in a product.
You don't want to drive in your car.
Yeah, exactly. So but that's the way you can find out what's happening at what's the frontier.
Yeah.
There are some software packages that people have developed which are open source and public domain, like OpenCV, which I think are a few years behind what the cutting edge is, but I think they are more easily manageable for people who are outside the field. So if somebody wants to implement some capability, it's not a bad place to start. To go look at OpenCV, see what kinds of modules they have, see if one of the modules there meets your needs. I think that's a good starting point. So so these are, I think, the two sort of inner and outer boundaries. What's there in OpenCV, that should be fairly easy for anybody to use, and it's a good starting point. That's one end. The other end is, okay, what's being published in the papers this year? And there's everything in between. And what's in between, a lot of the computer vision community now has made it a practice to put out code for their algorithms. So our community practice now is that generally when you write a paper and you have an algorithm, we publish the paper in one of these conferences, and on our faculty member or the student's website you put out the piece of software. Typically this will be MATLAB software. It won't be fast enough for people's applications, but you can download that, try it on some images and get a sense of whether this is going to work. You don't need to, so given where we are today, you don't need to start out by having to read the paper, implement the algorithm, and then see whether it works. That may put you back by 6 months, and with 60% probability it doesn't work for you anyway. Right? But if you can download the code from somebody's website, try it out, and then you know whether it fits or not. Remember, the field of computer vision is an empirical and experimental field. I do not have mathematical formulas which will tell me, okay, is this algorithm going to work on this class of images? Right? Sometimes you just have to try things out.
Yeah.
I think with experience you have a good intuition of where it will work or where it won't work. So I land up having to be an informal consultant to many different people who, for example, are scientists, okay, biologists. They are analyzing certain classes of images, and they want to find, let's say, examples of, this is like some data from some sample in a microscope, and you want to detect tuberculosis bacilli. Okay, now with a certain set of examples, you can see these are positive examples and these are negative examples, and we want to build a computer program which detects them. Now, because of my experience, I can say, okay, I think technique A will likely work on this class of images, or this problem is too hard. None of our techniques will do this. But even I, with my years of experience, will sometimes get this wrong, and I will not, in fact, be able to. So I always say, okay, my guess is that A will work and B will probably also work, but this is enough to try it out.
Right.
Okay, then you implement it or download some software, try it out, compute the numbers. Okay, it works at 90% accuracy, or maybe it works at 60% accuracy. Then the demand for the application may be that sometimes 60% is good enough, sometimes 99% is not good enough. So we kind of work out. This is, I think, the process we have to go through. We try out some choices, we look at, you measure how well you're doing, then you decide for the needs of the application or the task what accuracy is good enough.
Right.
It'll never be perfect, but for some applications, different applications have different accuracy demands.
Yes.
So that's the basic process. If you can get hold of an expert, they will probably have a good intuition about which technique is more likely to work.
Mm-hmm.
But at the end of it, you still have to implement or download and try it out on your data. If you don't have access to an expert, start with OpenCV and then work your way up from there. I mean, it may be that there is OpenCV software which does the job, but if not, it may well be that there are techniques which people have developed in the literature which do the job, but you'll have a slightly harder time working through it. Going through the literature is hard because it's a very active field of research, and I think as an outsider, grappling with the literature is hard because not all the papers are equally trustworthy, because researchers will develop their techniques and publish results, but certain techniques will work only for a very narrow class of images. Mm-hmm. And it isn't immediately obvious from reading the paper that is the case. So somebody who's not experienced in the field may think, oh, this should work for my problem, but actually it won't. Right. And you might spend a few months and have failure at the end of it. But that's reality. I think that when a field is very actively in ferment, this is the case. I think there are a few good textbooks. It's in the nature of the field that these textbooks are outdated pretty much by the day they are published. But it's still better to look at these textbooks than to just try to go through the masses of the mm-hmm. thousands of papers there are.
Right.
And I can recommend two textbooks. One is by Rick Zelinsky and one by Forsyth and Pons.
Okay, we'll put those citations on the website so people can find them.
So these are two current textbooks which kind of get at most of the current literature. But it's in the nature of the field that they will be outdated. Right. But I think working through these books may be better than working through 500 research papers, textbooks. That's the purpose of these textbooks. But it's the nature of our field that the subject is evolving very rapidly, and that these books themselves may be outdated.
No free lunch.
No free lunch. Yeah.
Fair enough. Well, this has been really fascinating. Thank you so much for taking the time to speak with us. Maybe I can just close with one last question, which is we've been talking a lot about how the field has evolved and where it currently stands today. Looking forward over the next, say, 10 years or so, what are you most looking forward to or hoping for or excited about in the field, whether it's in the research realm or the applied realm?
I feel that the rate of progress that we have seen in the last 10 years, I don't see it slowing down. I mean, in every field there are phases when you see that okay, now we seem to be running out of ideas and we are just beating around the same set of things, and then you kind of have to be in a pause for a little while, and then suddenly there will be some new idea and then there will be a breakthrough. Right now I'm seeing very steady progress, and if we continue at this rate, within 5 years or 10 years we should really have capabilities, the counterparts of face detection for many other kinds of objects. So detecting full people rather than just frontal faces. I think I'm not worried about the computational power needs anymore, because graphics accelerators as well as clusters of computing and for certain applications using the cloud and so forth means that we are no longer going to be held up by computing power limitations in terms of just developing an algorithm. If you want to deliver it for $100, it's a different question, mm-hmm. right? So I think we are no longer in research. I think we are no longer held up by computing power. I think we can get the computing power equivalent to what the human brain has. It's there today. So that is no longer a limitation. So we have access to lots and lots of data. So we have training examples of images of various kinds. So that is also not a limitation. So I think at this point, the research should continue to move rapidly, and as it succeeds in cracking some of these problems, I think the practical application will keep happening as we go along. It's very difficult to predict exactly what applications will come up. I think I'm not a believer in. Generally, people, when they make predictions, those predictions always turn out to be wrong. Because, for example, even 5 years ago, who would have foreseen that the Kinect would turn out to be one of these great applications?
Right.
It was not it was not the problem which.
Yes.
If you had asked me in 2005, I wouldn't have necessarily come up with that as a leading practical application.
Right.
Okay. But of course, if you told me, okay, what if somebody was trying to do this and they had this, I would say, sure, yeah, I can see why that is possible. But I wouldn't necessarily have thought of it in 2005. So there will be these kinds of applications which will take off. But I'm humble about my ability to predict those.
Yeah. It's not a linear progression.
Yeah. It's in the nature of really interesting applications that they are unpredictable. So I think that we should just have humility about that. But I see steady progress on the basic research, because the kinds of bottlenecks we faced 10 or 20 years ago simply do not do not exist.
So when you chose this field 30 years ago, was a good pick. In retrospect, you're in a good place at a good time.
Yeah, I'm lucky.
Well, we're very lucky to have this time with you, and thank you so much for this really interesting, really informative talk. Thank you so much.
My pleasure.